Hello, this is video number 19. I'm going to go over a special case of projectile motion in this video. We're going to talk about symmetric projectile motion. This is where the landing point and the launch point are the same level. You can see an object is launched at this location here, and then it arrived at this location here, which is at exactly the same height. So for this case of projectile symmetric motion, we have three special equations that we can use. This first equation tells us the time of flight, so the time for the object to go from the launch point to the landing point. The t equals 2v initial sine of theta over g, which you should be able to identify v initial sine of theta as being the y component of that initial velocity. And then we have the maximum height h, v initial squared times sine squared of theta over 2g. That's the maximum height that the projectile reaches. And then we have the range. As you can see in this picture, the range is the horizontal distance that the projectile travels. R equals v initial squared times sine of 2 theta over g. Now these equations are nothing new. They were derived from the kinematic equations. If, for example, if we go back to example 4, keep this equation in mind here for the height. Let's go back to example 4 that we covered in a previous video. You can see that when we found the maximum height using the kinematic equations, we got delta y equals negative VOY squared over 2a. So if you remember that, negative VOY squared over 2a, and then you look at this, VO squared, sine squared, that's just VOY squared, this numerator here, over 2a. The only difference is we used a, which was negative, and then we had a negative on top to cancel it out. This equation has a g. Every time you see a g in these equations, the g is a positive 9.8. So you can see the equations are identical. So there's a couple special things about one of these equations, the range equation. Remember, that's how far the projectile gets. The first special thing is that the complementary values of theta result in the same range. Complementary means that the angles add up to 90. So you can see here 75 and 15 add up to 90, and both of those, they get to the exact same landing point. They travel the same range r. Likewise for 60 and 30, you can see that those two end up here. So that's a special thing. The other special thing is that the maximum range happens when your angle is 45, as you can see from this picture. And both of these things come from just plugging in some theta values into this equation. For example, sine function has its maximum value when sine is 90 because sine of 90 degrees equals 1. That's the maximum value. So you can see that if you're trying to make this a maximum value to get the maximum range, well, 2 theta has to be 90. That means theta has to be 45. And then you can also plug in complementary values of theta in here and see that you get the exact same thing. Let's do an example with symmetric projectile motion. We have a golfer hits a golf ball with a speed of 60 meters per second at an angle of 50 degrees. Does the ball clear a tree that is 10 meters tall and is located 350 meters from the tee? Is the ball rising or falling? So the first thing I'd like to do is picture this example. So you have a ball that's being hit, projectile motion, and we don't know where the tree is. We just know that it's 350 meters away. So it could be over here, the first half, or it could be over here in the second half. So what I like to do is figure out what is the range of the projectile using the shortcut equation. So in the previous slide, we have range is v initial squared sine of 2 theta over g. V initial squared sine of 2 theta over g. Let's plug in our numbers in here. So 60 meters per second is our initial speed, and then theta is 50 here. So we're going to plug in 60 squared sine of 100 degrees, because it's 2 times theta is in the sine function, over g, which is a positive 9.8. Neglecting the units, they'll come out to be meters at the end. When I plug all of this in, I got 362 meters. So if that's the range, then if the tree is located 350 meters away, then we know that's more than halfway. So the tree is located somewhere over here. So the reason I wanted to find the range is because that already tells me that the ball is falling when it gets near the tree, because the tree is in the second half of the path. And now to answer the other question is that the ball, does it clear the tree? So the easiest way to figure this out is to figure out, well, what is the height of the ball when it reaches the location of the tree? Is that height more or less than 10 meters? And that will give us our answer. So for projectile motion problem, we're still going to have to separate x and y. We can't use any more of the special equations that we just talked about, because if we're looking at the ball right here, this is not symmetric anymore, because the ball here is not at the same height as the launching points. So let's write down what we know. In the x direction, we have v initial x is going to be 60 cosine of 50, which is 38.6 meters per second. And so in the y direction, v of y is going to be 60 sine of 50, and that's going to be 46.0 meters per second. We always know that ax is 0, that ay is negative 9.8. And let's see what else we know. Well, we're trying to find a height when the ball has traveled 350 meters. So we don't care about the range anymore. That was just to tell us if the ball was rising or falling. Now we care about delta x is 350 here. Where is the ball? What's the height at that time? What's the displacement at that time? So we have delta x equals 350. So in order to be able to find delta y, which is what we're looking for, we need to use the x direction to find the time. So I'm going to use the kinematic equation. Delta x is v o x times time. And in order to solve for time, I'm going to divide delta x by v initial x, divide 38.6 by 350, and I'm going to get 9.08. So I ran out of room a little bit here. 9.08 seconds. And now we can use this time for the y direction, because when the ball has traveled 350 meters, it took that amount of time. It's going to take that amount of time to get to that height. And now we have three variables in the y direction, and we can figure out delta y. So I'm going to use our most often used equation. Delta y is v o y t plus 1/2 a y t squared. Since I don't have much room, I won't plug in all the numbers, but they're right here. Multiply 46 by 9.08. Then you add 1/2 times negative 9.8 for the ay times 9.08 squared. That will give us a delta y. We got 13.6 meters. So that's the height, delta y, of the ball. Since the tree is only 10 meters tall, that means that it will clear the tree. So the second part of this example here says, what's the ball's speed as it hits the ground? So we know that it clears the tree, so we don't care about the tree anymore. We know that it's going to reach the ground here. What's the speed? So there are a couple ways to do this. I like to say the easy way and the hard way. Let's just do it the easy way. The easy way is to realize that this is symmetric projectile motion, and what happens for symmetric projectile motion is the same thing that happened when we had symmetric motion in free fall, which is that the initial speed and the final speed are the same. The only difference is the direction. This one's going up, this one's going down. Since we know that the initial speed is 60 meters per second, that's the final speed, 60 meters per second. Now, if you don't believe me, you're welcome to check it. I'm not going to do all the work, but you're welcome to use the v initial x that we found in the previous slide, which was 38.6 meters per second. And then you're welcome to solve for VFY using v initial y plus AYT. And then you know that your v final x is the same as your v initial x. So once you have VFX and VFY, you can plug them into the Pythagorean theorem and you'll get the exact same thing. But just save yourself some time. If you know it's projectile motion, then the speed does not change from the launch point to the landing point. Last thing I'd like to go over is a very fun question. My students always have very fun discussions when we do this in class. So, will the dart hit the monkey? A monkey escapes from the zoo. The zookeeper has a tranquilizer gun. So the monkey thinks, well, as soon as he fires this gun, I'll let go of the branch, I'll fall, the dart will pass over my head, I'm not going to get hit. But the zookeeper thinks, well, all I have to do is aim the gun straight at the monkey and that will hit him. So the question is, will the dart hit the monkey? This is projectile motion, so you neglect air resistance, and you do have to make the other assumption that the dart is fired with enough speed to reach the monkey, right? Because if it's just fired with very little speed, maybe it wouldn't even reach the monkey. So it definitely has to reach the monkey. So I really encourage you to click on this link to watch the video. MIT does a little demonstration of this and it's pretty funny and it only takes a couple of minutes. So I'll let you watch that. But I'll go ahead and go over the answer. So if you think about it, well, if he fires straight at the monkey, then this is the path that the dart would take if there were no gravity pulling that dart down. However, gravity pulls it down, and that's why the dart follows projectile motion. Sorry, this is not the best drawing here, but so instead of following a straight line, the dart goes down. So the point here, to make this as easy as possible, is that it goes down because it's in the air for this amount of time. Right? By the time it has reached a monkey, it has fallen down this much because gravity was acting on it for that certain amount of time. And guess what? The monkey fell at the same exact time that the dart was released. So that means that the monkey was in the air for the exact same amount of time as the dart. So that means that the monkey will fall that same exact distance and the monkey will actually get hit. So this concludes this video on projectile motion. I really strongly urge you that if you want to use the shortcut equations that we talked about here, really make sure that the motion is symmetric. It's possible that you have a problem where part of it is symmetric and part of it isn't. So don't just jump to these equations thinking that they're easier to use than separating the x and y directions. A lot of times you're still going to have to separate the x and y directions. Solve projectile motion by solving two one-dimensional problems separately.